With this section, we're going to be looking at what we are going to refer as direction fields. So we're going to be looking at graphs and getting an idea of the directions in which your functions is flowing based on equilibrium points. And then we're also going to look at a new method that is called Euler's method. All right, so let's suppose we have this differential equation. Okay, so again, we have this derivative function. Okay, it's in terms of y. And we want to see if we can find the solutions, all right, for this equation that are constant. Okay, so in other words, we want to find what we are going to refer to as the equilibrium solutions. All right, so basically all that means is we just want to simply find when your function, all right, is equal to 0. Okay, so this is kind of like saying your zeros. Okay, so we want to find when the function here, for what values is it constant. So all you simply will do is you're just going to take each of your factors and set them both equal to 0. Okay, so if we set the y minus 5 equal to 0, y plus 1 equal to 0, then we simply get y to be 5 and -1. Okay, so these are your constants where we have these solutions. Okay, now let's suppose we want to find the regions, all right, where the solution is increasing and then where it is decreasing. Okay, so kind of think about when we've done something similar to this before. We have here the 5, the -1. Since this is your derivative function, this is kind of should remind you of your critical points, right, where your function changes directions. So we want to know where is it increasing and then where is it decreasing. Okay, so we're just simply going to do a number line test. Okay, we're going to plug in values in each of these intervals and see what we get. Okay, so let's plug in something less than -1. So let's suppose we take -2 and plug it into this function. Okay, well, if we plug -2 into this first piece here, into this factor, what kind of number do we get, right? So a -2 minus a 5, that's going to be a negative number. Then let's suppose we plug in -2 here. 1 minus -2, that's going to be another negative number. All right, so if we multiply those together, then we get a positive number. Okay, so we are saying then our function, the region must be increasing, okay, anywhere less than -1. All right, now let's plug in something in between these 2 points. Okay, let's suppose we just pick 0. All right, well, do the same thing that we were just doing before. If I plug in 0 here, that's going to give me a negative number. If I plug in 0 here, that's going to give me a positive number. Okay, so negative times positive, well, that's going to be negative. So that means in between here, I am getting a negative number. Okay, my region is decreasing. All right, so now pick something here bigger than 5. So let's just pick 6. Okay, so again, plug it into your factors here. So plug in a 6 there, that's going to be a positive number. Plug in a 6 there, that's going to be a positive number. So multiply those together and we'll get a positive there. Okay, so that is telling us what's happening with our region. Okay, so we are saying that it is increasing where? Okay, so wherever we see those plus signs, that's where it's increasing. Okay, so it is increasing for anything that's less than -1, and then it's also increasing for anything that's bigger than 5. All right, so then where is it decreasing? It's decreasing anywhere between -1 and 5. Okay, so that's how we determine where the solutions, okay, what regions are the solutions increasing and decreasing. Okay, all right, well, now let's see if we can determine the initial conditions, right? So here, your initial condition, right? So make sure that it makes sense that we say, okay, t is 0. Well, what values, right, would a be? Okay, that's going to lead to those solutions increasing in time, okay, and then decreasing. Well, you just simply find out, okay, well, where is my function increasing? Where is my function decreasing, right? Well, what did we say before? Okay, well, that value, right, for which it is increasing must be bigger than 5, and then it also must be less than -1. Okay, so where did we get that from? We got that from right here. Okay, so bigger than 5, but then less than -1. All right, well, where's my function decreasing? Okay, well, we're going to grab that right here. So that leading coefficient has to fall somewhere between -1 and 5. Okay, so that's how we determine, all right, what that value A should be. All right, so then finally, we just simply want to see if we can decide what is the direction field, all right, that's going to verify everything that we just found, okay? Well, let's take a look at for part A, okay? We said that this is our equilibrium point, right? So that's what we found in part A. So that means when we look at our graph, that's going to tell us where our line segment should be, okay? So in other words, the horizontal line segment. So it should be crossing at 5 and -1. Well, if we look at this one, it is crossing at 5, but then here it's crossing at -2. You can kind of see what's happening here. Okay, so that's not what we want, so we're going to get rid of that. Then here, looks like maybe some changing is happening at 4, and then here we can see something is happening at -2, so it's not going to be that one. Then again, some changing has happened there at 4, and then some change has happened at -1, so it's not going to be that one. But remember, we said we wanted 5 and -1. So yep, you can see we have a line segment there at 5 and a line segment there at -1. Okay, so far that matches with what we got in part A. Then in part B, well, what did we say about where the function is, the region is increasing and decreasing, okay? So we said that it's increasing, right, when y is less than -1 and then bigger than 5, right? So less than -1, if we can see here, you can tell these pieces here, okay, these directions of those is definitely increasing, right, from left to right. And then you can't really see it with the one up here, but you can kind of see that the little segments are kind of going up, okay, the little pieces there. So that is matching with the increasing. Now, what did we say about decreasing? Okay, it should be decreasing in between -1 and 5. So you can see, yes, each of these little tick marks here, these little lines, you can see they are decreasing, okay? So therefore, this last graph over here, right, this is going to be the correct graph that represents the direction field. Okay, and then that's satisfied and is consistent with everything that we found here in part A through C. All right, so for this example, we are going to be applying Euler's method, and that's going to be this little concept that we have here. So it says for the following initial value problem, okay, we call this an initial value problem because you can see here we have the initial conditions here. We want to compute the first two approximations, U1 and U2, given by our Euler's method here, okay? So we are calling this our given step time, okay? So our function here is our differential equations, and then our change in t, all right, our step time here is 0.2. So we're just simply going to follow this method here, okay? Well, what do we know about u sub 0? Okay, that's our initial condition, right? So therefore our initial u sub 0 is just simply 4. And then we want to figure out then, okay, well, what can we say about this function here? So f of our t sub k and u sub k, okay? Well, that's just simply equal to, just taking our function here, is our 6u sub k, okay? All right, and so what we're going to do is we're going to let our k be 0, okay? So starting at the initial point. So therefore, let's see if we can find then our u sub 1, okay? Well, that's going to be equal to u sub 0 plus our function here, k, t sub k, u sub k, and then we have our change in t. All right, well, we said already that our u sub 0 was 4, so we're going to plug in 4 there. We said that our function here, k, is our 6 sub k, but then remember we're saying k is 0. So here we're going to replace that with 6u sub 0. And then we have our change in t, and we know that's just simply 0.2. All right, well, now all we have left to do is replace our u sub 0 here with our initial condition 4. Okay, so we're just going to put a 4 right there. Okay, and that is multiplying together. So 4 times 6 times 4, and then times the 0.2. Okay, so what do we get? 4 plus 24 times 0.2. So if we put all of that together, then we get that first approximation u sub 1, okay, using that method there is 8.8. All right, well, now we want to find u sub 2. Okay, so let's write out what that will look like. Okay, using our method here, so u sub 2, well, that's going to be equal to u sub 1, and then plus, okay, we know we have that 6u sub 1 here times our change in t. Okay. All right, so we know from what we just found in the first approximation, we know what our u sub 1 is going to be. So just going to replace that with 8.8. So 6 times 8.8, and then times our change in t. All right, and so just putting it all together, then we will get our second approximation, u sub 2, is 19.36. All right, so let's take a look at this example here. So we have, again, a differential equation, and we have it in the form of f prime or y prime of t equal to f of y. And again, we have an autonomous function, meaning that the function depends only on y. And then we have the constant y is equal to y sub 0. Okay, that's our equilibrium solution of the equation that provided that y sub 0 is equal to 0. Okay, so again, that's because we have the derivative, the differential equation is equal to 0. Okay, so we want to note, all right, so here is an important part here. We want to note that the equilibrium solutions correspond to horizontal line segments, okay, in our direction field, okay? And then we want to note, all right, then the direction field is independent of t, and so we now want to look at this differential equation here, y prime of t is equal to 5 cosine of y, okay? So we first want to just simply find all equilibrium solutions only on this interval from 0 to 2 pi, okay? So again, we say that equilibrium solutions corresponds to horizontal line segments, okay? Well, what does that mean? Okay, that just simply means that we want to find where our derivative function, okay, that differential equation, where it's equal to 0, okay? So remember, equal to 0 is like saying it's a constant function, right? So that's going to make a horizontal line if we think about that, okay? So that means then we want to find where our cosine 5 cosine y, where is that equal to 0? So of course, if we try to get the cosine by itself, divide both sides by the 5. And now we just want to simply know what must y be in order for our cosine to be 0. All right, well, we can just simply go to the unit circle and find where cosine is 0. So cosine is going to be 0 at the top of the unit circle, pi over 2, and then also at the bottom of the unit circle at 3 pi over 2. So here, this is going to be considered all of our equilibrium positions, okay, solutions that's in between this particular interval. All right, well, now we want to see then if we can see what the direction field is going to look like, okay? So we want to pick the correct solution, correct direction field, all right, on either side of the equilibrium solutions, okay? So that means we're going to have to kind of take a look at our solutions here. So if we think about what we have, okay, we kind of have three different regions, right? Okay, so we have something where it's less than the first solution, we got something in between, and we have something greater than. So we have three different regions that we're going to have to take a look at, okay? All right, so let's take a look at the first region, okay? So remember, we have to start at 0, so we want to go between 0 and then up to this first solution here. So from 0 to pi over 2, okay? So what we're going to do here is we're going to see if we can remember the acronym. Okay, if you remember the acronym, all students take calculus. Well, this is going to kind of help us with deciding if our function is increasing or decreasing, okay? Well, here we see that we're working with cosine. So we want to find out where is cosine. First of all, where is it positive and where it's negative, right? So if you remember the all students take calculus, cosine is positive here, and then cosine is also positive here, okay? So think about the unit circle, right? Here is 0, here is pi over 2, here's pi, and then down here 3 pi over 2, okay? Well, right now we're only looking between 0 and pi over 2, so that means we're looking here in the first quadrant, okay? And so there we see that cosine is positive. So cosine is positive, all right, from 0 up to pi over 2, okay? So that means then our derivative function, all right, is going to be positive in this first region. Okay, so we're going to see how is that going to help us in a bit when we get ready to pick our graph. Okay, all right, well, let's take a look at the second region. So our second region now, we're in between pi over 2 and 3 pi over 2. Okay, well, let's think about what that means in terms of our unit circle. So if we're talking about from pi over 2 all the way down to 3 pi over 2, well, what can we say about cosine? Well, we know cosine is positive in quadrant 1 and quadrant 4, but we see here in quadrants 2 and in quadrants 3, we see that cosine is negative, okay? So therefore, in this second region here, our derivative function is going to be negative. Okay, so then we got one more region. So here, let's say it's negative here. Then one more region now where we are now looking where y is bigger than this 3 pi over 2. Okay, so that means, well, of course, we're stopping at 2 pi, so that means we're now only just looking at what's happening here in this fourth quadrant, right? And so we said that, yep, cosine was positive, okay, in that fourth quadrant. So therefore, our derivative function is going to be positive here. All right, so let's go to our three choices of our graphs, okay? And let's put a plus here since we know it's positive, okay? So remember, we said our equilibrium positions were at these two values, okay? If we think about what pi over 2 is, that's approximately 1.57, and 3 pi over 2, that's approximately 4.7, okay? So look at our different choices here, okay? 4.7, that's a little bit below 5, so maybe that one. If we look here, that's kind of below 4, almost at 3, so it's not high enough for that one. And then here, this one's at almost below, almost at 5, so maybe it's that one. Then we have this other at the bottom here, pi over 2, so a little bit less than 2. And so, yep, we kind of take a look at this one, less than 2. That's too far down, and then this one's less than 2. So we know we can for sure get rid of the middle one, okay? So now all we have to do then is just decide on the directions, right? So if we look at in between, you can see all the line segments in this one. You can see here it's going down, here they're increasing, and here it's going down. But it's opposite for this one over here, right? They're increasing there in between that region. This region, you can see the little line segments are going down, and then in this region, they're going up. Well, what did we say that we had over here? We said in that first region, our derivative function was positive, okay? So that means between 0 and pi over 2. So below pi over 2, the little line segment should be increasing. And yep, we can see here they're increasing, but over here they're decreasing. Okay, so it looks like it's not going to be that first one. Then what do we say? In between pi over 2 and 3 pi over 2, so that third region, we said our derivative function was decreasing. Okay, so we can see, yep, they're coming down here, but over here they're going up. So it looks like it's not going to be that first one. And then after 3 pi over 2, we said the derivative function is increasing. Okay, so yep, everything bigger than that 3 pi over 2, we can see that it's increasing. And here it's decreasing, so it's not going to be that one. So therefore, the correct direction field for that particular equilibrium solutions right on either side is going to be that last one there. Okay. All right, and then let's see if we can pick the correct solution curve, okay, that corresponds to that initial condition y of 0 equal 4, okay? Well, basically all we're going to do here is kind of think about, all right, what are we saying here? Okay, so here we have y of a, let's just pick some variable, right? Y of some value a is equal to capital A, right? The solution. So basically, we're going to just kind of compare that to what we have, okay? So therefore, we have y of 0 is equal to 4. And what that's going to do is help us with where to start our curve, okay? So basically, we're just simply going to start at the point 0, 4. Okay, that's where we're going to start and then see what's happening in between that particular region. Okay, so we're starting at the point 0, 4. So you can see here that one looks like it started at 4. This one starts at 4, but it's in that third region, right? So that's the third region, that top region. So we know it's not going to be that one. And then when we look at this graph, it does start at 4, but this one is increasing in this region. This one is decreasing in this region, right? Well, what did we say we had up here in this graph? In between that region, you can see we said that we are decreasing. Okay, so which one should we go with? In this region here, you can see that this little line curve, that solution curve is decreasing there. So this one is going to be the correct solution curve that corresponds to that initial condition.